Hey guys, so in this video we are going to talk about the CVS physiology, that is part 2. In this video we are going to cover the hemodynamics part. So that is hemodynamics. This is the most conceptual part of the CVS as it involves some physics and all the principles related to the fluid dynamics. So first we have to see what is blood flow and blood velocity and how both are calculated. So velocity means we know it is a distance an object moves over the time. For example, in blood, this measurement is often given as centimeter per second. So how much blood is traveling per second. So how much centimeter the blood is going to travel per second, this is the velocity. So in unit time, how much distance are you going to cover? Now, flow refers to the movement of a volume of a liquid or gas over time. So it is also unit time concept, but here we are measuring by the volume. So how much volume of blood has moved in a unit time. So this is more like a three-dimensional concept. Here the velocity was kind of one-dimensional concept, that how much distance are you just going to cover, and in this how much total volume is volume of blood has covered in unit time. So if this is a velocity, then it is distance per time, and if this is the flow, then it is a volume of blood that is travel upon the time. Now you can measure that blood flow is change in the pressure upon the resistance. As we know, there is Ohm's law that we have learned in the electrodynamics that states that any flow of the any current that is passed is difference of voltage upon the resistance. So this is the Ohm equation, and from this we have derived this equation. So it is same, this two is flows and this is pressure difference, and here it was voltage difference, and this is resistance. So we have derived this equation that blood flow is equal to pressure difference upon the resistance. Now there is Poiseuille-Hager law, which states that the resistance is directly proportional to the length that has to covered, and the diameter square, inversely proportional to the diameter, not square but raised to 4. So diameter means the radius raised to 4. So by this equation we have calculated the resistance part, plus also this fluid viscosity. So resistance is equally proportional to the fluid viscosity. So we have like these three things: fluid viscosity, then length and the radius, and these two are constant, so 8 upon pi. So we have this calculated this resistance. Now we are putting it into this equation. So flow is directly proportional to the pressure difference and directly proportional to the diameter raised to radius raised to 4, and upon viscosity and length. So we got this equation. Now if we see the velocity, then it is, so the here it was flow, but now here it is velocity. So we have to divide by the area, because we know that velocity is equal to blood flow upon area. So we got this equation that velocity is going to proportional to the area upon viscosity upon length, but velocity of flow is inversely proportional to the cross sectional area. I am not able to understand how actually this is related. If you know, then you can explain to me. So this is one thing we have to remember. So first, about the Ohm's law, that is I is equal to V upon R. Then we have derived the blood flow, that is delta P upon R. Then we derived that R is equal to delta P upon Q. That is actually mmHg upon milliliter per second. So you can derive like this, that it is a peripheral resistance unit, and if you put the liter part, so mmHg upon liter per minute, then it is Wood's unit. So here this 2 unit. Now velocity of flow is inversely proportional to the cross sectional area. So this thing, velocity of flow is inversely proportional to the cross sectional area. That's why the aorta has very small diameter compared to all the capillary networks. Here we are not talking about the single capillary, but okay, I am going to write here only. So aorta has 4.5 centimeter square of diameter, while the capillary, whole the capillary network has this much of diameter. That's why, so we have learned that velocity is going to inversely proportional. So in this, velocities will be too much, so increase velocity, and here it will be very less velocity. So if increase velocity, it is going to be a turbulent flow of blood, and if decrease velocity, then it is lamellar flow. So now we are going to discuss the lamellar versus turbulent flow. So lamellar means, as the name suggests, it is going to flow in the layers. So in center part, the velocity will be more, and in peripheral part, velocity will be less, and it is silent. There will be no voice in lamellar flow, as the velocity is less, and turbulent is totally different. It will be irregular, so in every direction blood is going, there will be just no shape, and here it won't be silent, so noise or sound will be there. Now we have to see at which velocity there will be this laminar flow and turbulent flow. There is a critical point, critical velocity till which the flow will be laminar. And if we are talking into Reynolds number, then it is less than 2000. Now here it will be more than 3000 Reynolds number. And if velocity is more than critical velocity. Now what about this two number, in between this two number? So between 2000 to 3000 there will be transitional flow. Now we are going to learn about the Reynolds number calculation. So I have already written this part about the linear and turbulent flow. So this is the Reynolds equation. Reynolds number we can calculate from this. So the more velocity, as we can see here, this was also criteria about the velocity. So we already know that if velocity is going to increase, Reynolds number is going to increase. Now this two term we have to remember that this is about the density and this is about the viscosity. So more the viscosity, Reynolds number will be less, and more the density, Reynolds number will be high, plus more the diameter, Reynolds number will be high. Now I really don't know why this is like this, that velocity and density, increased density has more Reynolds number. I really don't know, but we have to mug it up. We don't have any options. So viscosity, density and diameter. Again, diameter is increasing, Reynolds number is going to increase only. And here also the velocity was inversely proportional to the viscosity. So viscosity is still understandable, that with viscosity, if the fluid will be very thick, it won't have much velocity, plus the Reynolds number will be also low. This too is quite understandable, but this density and diameter part I am not able to understand, that why these two are related this way. And if there is increased viscosity, maybe there will be increased density also. So really don't have any idea, but you can just remember this two, and remember that density and viscosity are other way round. So if Reynolds number is inversely proportional to the viscosity, then the density would be directly proportional to the Reynolds number, and diameter will go with density only. Now about the Bernoulli's law. So Bernoulli's law says that total energy is equal to kinetic energy plus potential energy plus pressure energy. In physics we have learned about this too, that kinetic energy plus potential energy is equal to total energy. I don't know why they have also put this pressure energy extra. So let's see, in supine position what will happen, that our potential energy very low. In physics we have learned that potential energy will be increased as we move from the ground. So the more high we are in the ground, we have the gravity pulling towards it. That's why the potential energy will be increased. So the potential energy will be zero when we are touching the ground, I mean in supine position, and kinetic energy will be maximum. And the pressure energy is the lateral pressure energy, the force with which blood strikes the lateral wall of the vessels. Now what will happen that suppose here is an atheroma, ठीक है, and A1 is total diameter and A2 is diameter after we have reduced the space of atheroma. So the diameter will be less, I mean the area will be less, so A2 is gonna be less. So what will happen at this point and in this point? So in A2 the kinetic energy will be more, but the pressure energy will be less. So flowing blood can never dislodge an atheroma. And why kinetic energy will be more in A2? We have just learned our application that velocity is inversely proportional to the area. So less is the area, more is the velocity. So less is the area, more will be the kinetic energy. So this is our second application till now of the velocity rule we have derived. Actually first was about the laminar flow and turbulent flow where will be seen, and the second application is about this, if this can dislodge the aneurysm and atheroma, about the Bernoulli's law. So as you can see here that in this the energy will be low but the pressure energy will be less. That's why flowing blood can never dislodge the atheroma. Now what will happen in the aneurysm? Totally different. That here the kinetic energy will be less but the pressure energy will be more. That's why there is risk of rupture is very high. Now the last law that we have to remember is Laplace law. So let's see. This is actually tough for me, this Laplace law. I am never able to fully understand the concept. So this is a cylinder and this is a sphere. So what will happen that the radius of curvature here will be 1 only and here will be 2 radii. It is a plural form of radius of curvature. Now the wall tension is equal to the distending pressure into radius. So this is distending pressure Now what will happen in alveolus, that the tension force is distending pressure into radius upon 2, and in the ventricle tension is equal to pressure into R into 2W. W is a width that we put for the thick structures. Here it was a thin structure. So if the distending pressure here, if in ventricle it will increase, then the width also has to decrease. So there will be concentric hypertrophy seen.